Okay, what is light? Well, light is the agent, right, that allows vision to happen for us humans, but it's actually a part of a much broader thing called the electromagnetic wave. And the sun produces electromagnetic waves. In fact, the most common waves, frequencies that reach Earth's surface, is what we see as visible light. And it's likely that mankind evolved to see light because these are the most common frequencies from the sun. But is light a particle or is it a wave? Right? And this is a debate that goes back to the 1600s. And evidence of the wave theory is validated with the discovery of even more wave types by the 1800s when radio waves and infrared were discovered. And really, it's just a difference in wavelength. And that's why it's called a spectrum, which you start from radio waves, which have a very long wavelength, and you go to the other end of the spectrum, and you have gamma rays with a very short wavelength. And there in the middle, you see the visible part, which is light. Now, there's also evidence for the particle theory, and this was even more validated with the photoelectric effect that took place by the late 1800s. And light as a particle with quantum energy would later be explained in the early 1900s by Max Planck and Albert Einstein. By the 1900s, though, it's considered now to be both, and has for a century. So it is both a particle and a wave, and it's a phenomenon known as wave-particle duality, and it's called the photon. And the photon is the carrier of the electromagnetic force. Basically, everything that you saw on the electromagnetic spectrum is carried by what's called the photon. And this is one of the common explanations for a photon, right, which is an electron can move closer to the nucleus of an atom. It's a lower energy level, and when it does, it emits a photon. All right, that's the common explanation. Well, let's try to get to something a little bit simpler that matches experiments. So photons are really transverse waves of energy as a result of particle vibration. So here it is again, the typical explanation where an electron moves closer to the nucleus of an atom and it generates a photon. And in this particular case, if it vibrates as it gets closer to the nucleus with a frequency that would be visible light, that is what we can see with our eyes. Now, we can't see radio waves, but they happen. And it happens in all sorts of electronics, from the radio in your car to the cell phone. And this is really just a vibration of electrons in an antenna that is creating the radio waves. Now, the funny thing about this is radio waves actually appear more like waves than they do particles. It's a continuous wave. And that electron is constantly vibrating in an antenna. Now, it doesn't have to only be vibration of electrons. Entire atoms can vibrate too. And this gives off many different wavelengths, including what we can see as infrared with the help of goggles. In fact, if you are really heating up something like a frying pan, if it gets hot enough, it gets even beyond the infrared and starts to turn red. So something that is now in the visible wavelength that we can see. And temperature is simply a measurement of the average kinetic energy, how fast these atoms are vibrating. So the faster the vibration, the shorter the wavelength. Well, let's put this together, though, for a really simple explanation of light and photons. And for this first part, you have to go back to some of the other videos in energy wave theory, but particles are reflecting, the core of a particle is reflecting longitudinal waves, right? An in wave becomes an out wave, and that creates the standing wave structure of the particle. But now, as that particle vibrates, it creates a secondary wave. And that secondary wave is a transverse wave to go along with the longitudinal wave. And those are the two different parts that we see in the electromagnetic spectrum, which we see as electric and magnetic. Now, if the vibration is short-lived, right, such as when the electron is settling into a new orbital, that wave looks more like a particle, a bundle of energy. But if the vibration is continuous now, such as a radio wave, that transverse wave looks more like a traditional wave. And here it is all put together. It's actually more like a dipole, but this is an example of what radio waves would look like if we could see them. And that's it. I hope that sheds a little bit more light on photons.